Okay, so hello everyone. I welcome you all to this lecture. So, in the previous class, what we have seen is we have seen the Fourier's law of heat conduction, which states that the rate of heat transfer is nothing but the product of the thermal conductivity with area and the temperature gradient, that is dT by dx, right? And then we also saw this generalized energy balance equation, which is in vector formation. We can write as dou 2t plus q dot by k is equals to 1 by alpha del T by del T, where this capital T stands for temperature and this small t stands for time. And this Laplacian we can write in different in different coordinate system. In Cartesian coordinate system, this simply can be written as dou 2t by dou x square plus dou 2t by dou y square plus dou 2t by dou z square. Whereas in cylindrical system, this is the expression for this Cartesian system. This is the expression for Laplacian, second order Laplacian, and this is for the spherical system. And this Laplacian is operating on this variable temperature T. Okay, and this q dot is the rate of is the volumetric rate of heat generation. Okay, is the volumetric rate of heat generation, and k is the thermal conductivity, and alpha is the thermal diffusivity, which is k by rho cp, right? Which is nothing but k by rho cp, right? Okay. So now we also saw, in addition, we also saw different type of boundary conditions. These are, for example, constant temperature boundary condition, which states that the temperature at any particular surface is nothing but some value. Then constant flux boundary condition, which is which could be something like this: k into dt by dx equal to 0, or rather it should be minus k into dt by dx equal to 0, right? It should be minus. Okay. So this boundary condition basically corresponds to an insulated surface here, right? Okay. Non-zero flux boundary condition, wherein we have some positive value of flux, like for here example, here is the zero flux boundary condition and here is the non-zero flux boundary condition, and this constant could be anything, for example 10, 100, or any numeric value, or it could, when this is when the so that would be a non-zero flux for constant flux boundary condition. And this the third and the last boundary condition is the variable flux boundary condition, in which this flux is a function of temperature. Okay, like this, right? After that, we studied about Newton's law of cooling, which is basically a constitutive relationship to describe the flux inside a fluid. Okay, so Fourier's law is a constitutive relationship for flux inside a solid, whereas Newton's law of cooling is the constitutive relationship to describe the heat flux inside a liquid or a fluid. Okay, and then we also saw that at this surface, whatever heat flux which is coming from solid is described by this purple color expression, minus ks into dt by dx, whereas ks is the thermal conductivity of the solid, and dt by dx is the temperature gradient inside the solid. Okay, and now this h is nothing but the this h into ts minus t infinity minus ts is nothing but the Newton's law of cooling, which gives us the flux inside this fluid. And this minus kl into dt by dx is nothing but the flux at this boundary. Okay, so kl stands for thermal conductivity of liquid, and dt by dx is at the this end. Okay, so now note that this since this ks and kl, these are different, so are the temperature gradients respectively. Okay, now usually ks is greater than kl, so the temperature gradient inside the slab would be in general greater than the temperature gradient outside the slab or inside the fluid. Okay, so we ended that. Then we went on to study the one dimensional steady state heat conduction without any area change, or without any area change, or without any heat generation. So we saw that this expression is only applicable when our system of consideration is isotropic and it has a constant area and there is no heat constant area, right? So we solved the this expression, right? So we this is the generalized expression. We wrote a one-dimensional form, and then we solved this equation, and we found out that flux rate of heat flux is given by this expression. And then we also studied about the resistance concept, which tells us that the resistance of this particular system or this lab is nothing but the overall the overall driving force divided by the heat transfer rate. So this is analogous to electrical resistance, wherein the current flows inside a resistance, current flows inside a circuit, and the resistance of that circuit or resistance offered would be given by the Ohm's law. And okay, so here we have and there the gradient would be the potential gradient or the driving force. Here the driving force is temperature gradient divided by the rate of heat transfer. Okay, so current is analogous. So in that aspect, the heat transfer rate is analogous to current. Temperature gradient is analogous to a potential difference, and resistance of conduction is analogous to resistance offered by or the ohmic resistance. Okay. Now we also studied. Okay, so that's we also studied about this system in general. Okay, and that's where we and then at the end we stopped with looking at composite wall like this, where we have a multiple walls or a wall made up of multiple materials which could act as an insulating surface, where which could like for example here, let's say there is a chimney through which a hot gas is flowing, let's say a hot flue gas, and then we have to design a wall which could prevent the heat loss through this fluid, and this is the ambient temperature. So we studied about this overall resistance concept, and we quantified the or we wrote down the resistances for each of these things. So this L by Ka is nothing but the conductive resistance, what we call, and you are usually related with the Fourier's law of heat transfer, whereas this conductive 1 by Ha is the convective resistance. Okay, and which are related to the um, Newton's law of cooling. And then we also, so this was our thing, and then we also proved it, we derived it that this is indeed true. Okay, so in today's class, what we are going to study is, so up until now, what we had a one-dimensional system without any change of area and without any without any heat generation. Okay, so now here what we are going to study is we are going to study something called as an heat transfer coefficient or overall heat transfer coefficient. Now in practice, what we have is, uh, let's say for example, this is the temperature. Let's say this is the temperature, this surface temperature. Let's say this is T2, this is T3, and this is T4, and this is T infinity 2. Let me change a color. This T infinity 2 and the infinity 1. Now in reality, though we wrote all these resistance concept, we wrote that these are the individual resistances, and the total resistance is nothing but sum of individual resistances, and R total we could write as in these individual resistances are nothing but 1 by H1A, 1 by H1A, LK, so on and so forth. Right? So this is the overall resistance. Now in reality, we are not aware about let's say the question what we have to find is we have to find out the temperature distribution throughout this part, right? So in reality, what information has been given to us in practical applications, we usually know what is this T infinity 1, which would be the bulk temperature of the hot fluid, and we would also know the ambient temperature of the cold fluid, right? This T infinity 2. And then we would also be knowing this Ka, Kb, and Kc, right? So now what we want to do is we want to, since we do not know in practical scenarios what is this temperature, these intermediate temperature, now somehow we would want that we could describe the entire system using measurable properties. Now in this case, the measurable properties would be this T infinity 1 and T infinity 2, right? And additionally we also know that this is Ka, Kb, and Kc, but we would want something in terms of this T infinity 1 and T infinity 2, because it's easier to uh, calculate or measure, right? So that's where our concept of overall heat transfer coefficient come. So now overall heat, so since there is no heat generation and change in surface area, the cross sectional area remains the same. We can write something called as an overall heat transfer coefficient, wherein we define the total rate of heat transfer as a function of u, something called as u, which is the overall heat transfer coefficient, and area. So now since area here is same, the area for this overall heat transfer coefficient is also going to remain the same, right? So UA into T infinity 1 minus T infinity 2, right? So we could measure this thing. This is a measurable property. Okay. Similarly, this is also measurable, right? And this is what is we call, or rather, this U is what we call overall heat transfer coefficient. Okay. And then as per our As per our nomenclature, this Q is nothing but analogous to electrical circuit. This Q is the current, and the driving force for this thing would be temperature difference, and this is the R total. So hence we can write, R total is equals to 1 by UA, right? But this 1 by this R total is also, we know, this is nothing but this, right? So from these two expression, what we can say is 1 by UA is equals to 1 by H1A plus L1 by K1A plus L2 by K2A plus L3 by K3A plus 1 by H2. Okay, and then we call this U as an overall heat transfer coefficient. Now, since our system here has a constant cross-section surface area, right, and hence this area remains the same, and hence we can cancel it out, as well. However, if you consider systems such as, let's for example, a cylindrical system. Let's say, for example, like this cylindrical system. Okay, and let's say that the heat is transferring from inside cylinder to outside cylinder. Now, in this case, the cross-sectional area changes. Hence, or let's say, for example, this is one cross-sectional area. Let's say this is A1, and let's say this black one is A2. So now, because these areas are different, in principle, we can have multiple, or in this case, two types of overall heat transfer coefficient based on this area and based on this area. Okay, that's what we'll cover in the upcoming lectures, right? In the future lectures. Okay, so now there is one this concept of contact resistance. Now, what happens at the microscopic level? Now, at the macroscopic level, what we assume that is, these surfaces are entirely exactly um, are in perfect contact. Perfect contact means there is no air gap, or there is no discontinuity when these two surfaces are in contact, right? But in reality, that would not be the case. At the microscopic level, there is nothing called as exactly smooth surface. So there are going to be some irregularities at this interface, or at this interface, or at this interface. Now, how do you account for that? You account first. You account it by using something called as contact resistance. Now, contact resistance would nothing but, since there is no perfect contact between this, now this is going to just contribute to an extra resistance for the system. So here for this system, where we assume a perfect contact, we have something. We have five resistances, right? These are the five resistances. However, when we assume that there is some contact, there is some mismatch in contact, then we would just add an extra contact resistance, and then overall for this entire system, we are going to get six resistances. One would be for this, one would be for this, like like we had in here. One for the hot gas, one would be for the for the first slab. And then we here additionally we would have a contact resistance, then for the resistance for the second slab, third slab, and convective resistance for the outside fluid, right? So now, what we are going to delve today, okay, I hope this is clear to everyone. Okay, let me just, yeah. So now, up until now, like I'm repeating this again, but it's very important for to have a certain sort of certain repetitions are good, because that helps you concentrate and remember what you have covered. Okay, so now, up until now, what we have covered, we have used generalized energy balance to calculate the temperature profile, heat transfer rate, so on and so forth, for a one-dimensional system, and without any change in cross-sectional area, and without any heat generation. Now, today's class will increase will move away from this simplistic system to a realistic system, and the first thing, and will be increasing the complexity of the problems which we are going to solve. So the first complexity which we are adding for today are the varying cross section area. So here you consider a system that heat is getting, let's say for example, is let's say T1 is greater than T2. Okay, T1 is greater than T2. So in that sense, and all these areas are insulated, so it's only one dimensional. We are still considering one dimensional heat transfer. Okay, right? So rate of heat transfer, so heat is going to get transferred from in this direction, right? Heat transfer. But here you see the cross sectional area at each at each location is going to change, right? So how do we incorporate this and solve for temperature distribution inside the system? Okay, now the in generalized energy balance which we had, was dou 2t, right? Here, since this is an cylindrical system, so let me first describe the system. So what we have is, we have a cone or a frustum of cones kind of structure, right? So here we are maintaining this face. You can imagine a face like this. So for example, it is like this and one more here. Okay. So let's say this phase of this frustum of cone is maintained at some temperature T1 using some sort of a somehow we are able to maintain temperature of this entire surface, entire circular surface at temperature T1. And let us assume that the axis, okay, so this is the axis what we are assuming, this is the axis. Okay, so this is x direction, this is 0, and this is r direction. Okay, so now here what we have is, at certain x equal to x1, we are maintaining the temperature at temperature T1, and at x equal to x2, the temperature is T2. And now what we are asked, and we are also given that this T1 is greater than T2, and what we are asked is, we have to compute the temperature distribution as a function of so it's very important to remember that temperature here is going to be a function of only x. Now, why would that be? That is because we are assuming it's a one-dimensional heat transfer. So we are saying that the heat is getting transferred only in this direction. So how that is going to happen? That would happen only if the entire cross-sectional temperature remains the same. So for example, this is one cross-section. Let's say this is one cross-section. This is another cross-section. So the temperature is varying only in x direction, and the entire temperature in r direction is the same. Okay, that is what we are thinking about one dimensional system. Okay, so now generalized energy balance for this system, right, is nothing but dou 2t. Here what we are going to use a cylindrical coordinate system plus q dot by k is equals to 1 by alpha into dou t, derivative of temperature with respect to time. Now since we are saying one dimensional steady state heat conduction, right, the moment we say it's a one dimensional steady state, or the moment we say it's a steady state, we can assume this as 0. Okay, then we have one dimensional also. So in one dimensional, okay, so first of all let me just say that we cannot use this expression. Now why this expression we cannot use? If you remember in our first lecture, we explicitly mentioned that the limitation of this expression of the generalized energy balance is that we are assuming that the cross sectional area is going to remain same, and we also assume that the this that the material is that the thermal conductivity of this material is same in all the direction, right? So that's an iso, I think the thermal conductivity remains same in all the three directions, right? So in this case what we are going to see is, since the moment we say that it's a one dimensional heat transfer, we can simply go back to our constitutive relationship. Since this is a solid, we are going to use the constitutive relationship of which for solids, which is nothing but Fourier's law of heat conduction. So in that case, since I said it's a one dimensional, so q is only going to vary in x direction. So q is equals to minus k into area in dt by dx, wherein here now we are going to say that area is a function of temperature. Okay, area is the function of this x direction, right? So area actually is function of r, and then r is going to be a function of x. That's what we are going to assume. And then simply let us assume that this area as a function of x is nothing but pi into r of x square, right? And this r, let's say this r of x is nothing but a of x, right? So we just plug in this qx is equals to, instead of area, we are just going to, let me just you know instead of this area, we are going to assume that area is nothing but pi x square, pi r square, and r is going to be a function of position in the x direction. And then that r is, let's say for example, we assume that r is equal to a of x. Then we can simply replace pi ax square, and this is going to be a simple expression for differential equation in in only one variable, right? It's a second order, it's going to be a second order differential equation, right? So we just rearrange it, and then we end up with something called as an this expression. Okay, and then we integrate it out, and we end up with, okay, and then we just integrate it out, and then we integrate it out two times, and then we end up with this temperature profile. Okay, we end up with this temperature profile. Now since this is like after one integration, and then here we can use boundary condition. Now what is the boundary condition? Boundary condition will be at x equal to x1 we have temperature T as T1, right? So we just include this into this, and then we calculate the value of C1, which corresponds to be this, and then finally C1 and C2 we compute, and then we end up with this temperature distribution as like this, that T is equals to Q of x divided by K pi a square into 1 by x minus 1 by x1 plus T1, right? So this is the temperature distribution we end up with. So so now we have gotten the temperature distribution. Now what is the intuitively or intrinsically next step which we have in any sort of a question? The next step which we are going to have is, once we compute temperature distribution, we are going to calculate the rate of heat transfer. And how we could calculate the rate of heat transfer, right? Using this second boundary condition at x equal to x2, we can use this second this thing, what is it called, second boundary condition, and we end up with this rate of heat transfer is going to be nothing but this, right? So we put equation this expression into our original expression for temperature distribution. Why? Because here you see the temperature is going to be a function of Q of x, which is the rate of heat transfer, and we do not want it, because all the other things we can measure, but Q of x is as of until now, we don't want to, we want to eliminate this Q of x from temperature profile, this thing, right? We just put in this value, and then we end up with this temperature distribution, right? Temperature or the temperature at any location x is nothing but T1 plus T2 minus T1 divided by 1 by x2 minus x1 multiplied by 1 by x minus 1 by x1, right? You should always remember that here, since this temperature is a function of x, and you should convince yourself that this flux, remember, it's not the we are not talking about rate is going to remain constant, but the flux is going to change because the area is going to change, right? Flux is what? Flux is nothing but rate divided by area. Now, the rate of heat transfer, or analogously, you can assume the current through the circuit is going to remain same, but the flux of heat transfer, that is the rate per unit area, is going to change. Why? Because area is changing with respect to x. Okay, so flux is going to be a function of x or r, whatever you say. Right? So you should convince yourself that flux, which is given by this expression, minus k dt by dx, is not constant. In fact, it's going to be a function of x, and which is very clear because this dt by dx we have already calculated, right? Here we calculated somewhere that dt by dx is nothing but a minus qx into, it's a function of x, right? So now because of this flux is also going to be a function of x. Okay, just a second. Anybody has any doubt, they can ask, or we'll move ahead. I hope this is very clear. How do you incorporate a change in area? How do you incorporate a variational area or change in area in our calculation? How do you solve this kind of a problem? Okay, this kinds of problem. Okay. So if this is clear to everyone, we'll move on to the next thing, which is which we are going to study for radial systems. Okay. So now this is a radial system. Let's say a radial or cylindrical system. तो इसमें क्या है? We have a one cylinder, a concentric set of cylinders. So this is blue one is one set of cylinder, and inside it we have another cylinder. Okay, it's like this system, or it's a cylinder inside a cylinder. Okay, cylinder inside a cylinder. So blue one is the outer cylinder and the green one is the inner cylinder. The radius of the outer cylinder is R2 and the radius of the inner cylinder is R1. And this in the whatever space is there in between these two cylinders is filled with some material. Okay. Now usually that material, the conductivity of that material we are assuming as K1. Okay. So there is no. So what we need to do is always we need to do in any heat transfer problem. First we need to calculate the temperature distribution. Second, we need to calculate what is the rate of heat transfer, and third, we need to calculate what is the flux of heat transfer. Okay. So now, just we are just what we have been given this system, and temperature has been given. This has been maintained at temperature T1, right? This inner cylinder, the outer surface of this inner cylinder is maintained at some temperature T1, and the outer or inner surface of this bigger cylinder is maintained at temperature T2, right? And usually, or let's for assumption purposes, we'll assume that T1 is greater than T2, so heat is getting transferred from green cylinder to blue cylinder. Okay. So now what we need to do is we need to calculate temperature profile, rate of heat transfer, and flux of heat transfer. Okay. So now the assumptions what we are going to do is we are going to assume that it's a one-dimensional flow. So temperature is going to vary only in this direction, Z direction. Okay. Oh, sorry, R direction. Okay. We have an isotropic system, and surface area, is going to is same. ठीक है क्योंकि heat transfer ऐसे हो रहा है तो surface area is going to remain the same. Okay, so now here we say what we are interested to calculate. We are always interested to calculate what is the temperature distribution, what is the heat flux, and what is the rate of heat flux. Okay, so now we are going to use, since the cross sectional area is same, and we have an isotropic system, we can use generalized heat balance equation, right? But here what we have is it's a one dimensional steady state. So as soon as I say steady state, this term goes away. As soon as I say one dimensional, couple of terms from here goes away, and then heat generation is zero. So this term also goes away. Okay, so now finally, okay, so this is the Laplacian which we had. This I have taken from previous slide. Okay, so for a cylindrical system, this is our cylindrical Laplacian for cylindrical system. We said that it's a one-dimensional system, so the temperature is going to be a function of R, and then that is why, because of this goes to zero and this goes to zero. Or for example, here you can see this is equal to zero. Okay, now what is this? This is, but this del 2t is equal to, because this is zero, because there is no heat generation, and this is also zero. So essentially, ये है del 2t, this is 0, okay, because of heat generation, and ye bhi 0 because of steady state. So del 2t, finally what we have del 2t is equal to 0, and del 2 here is this. ठीक है, तो इसका मतलब हो गया that 1 by r, here you see 1 by r dou by dou r, so this operating on temperature as a variable, r into dou t by dou r plus 1 by r square dou 2 t by dou theta square, dou phi square plus dou 2 t by dou z square equal to 0. Now since we say it's a one dimensional system, we can just eradicate these two expressions as well. This is also going to be 0 and this is also going to be 0. Okay, so what we end up with this expression, 1 by r dou by dou r into dou t by dou r is equal to 0. Now this is a second order differential equation, and we need two boundary conditions. I already mentioned that we know the surface temperature of this green cylinder as well as surface temperature of this blue cylinder. ठीक है, so we just use those boundary condition कि r is equal to r1 पे temperature T1 है, r is equal to r2 पे temperature T2 है. ठीक है, so now you just multiply both the side by r, so we and then and then we take अगर r से multiply कर दोगे तो क्या आएगा, you will end up with dou by dou r into dou t by dou r is equals to 0. अब इसको इंटीग्रेट करोगे तो क्या आएगा, r into dou t by dou r is equals to some constant which is this one. ठीक है, now you just rearrange it, dou t by dou r is c1 by r, तो टेम्परेचर तुम्हारा क्या आ जाएगा, टेम्परेचर आएगा c1 ln r plus c2, where this c1 and c2 are the constant of integration. Okay, Then we use the two boundary condition which we had, that at R is equal to R1, temperature is T1, okay, and at R is equals to R2, temperature is T2. And then you so we have these two linear equation. There are two variables, so you can easily solve it. I have done the math. I'm not going to explain it. Again, essentially तुम्हारा temperature profile आ जाता है ये. So this is the temperature profile which we are going to see, that temperature T is equal to T1 minus T2 divided by ln of R1 by R2 into ln of R by R2 plus T2. So now here at any R we can calculate temperature as this. Okay. Now what is the next step? Here you see the next step. Once we get the temperature profile, so this we got. Okay, what is the temperature profile? Temperature profile मिल गया. उसके बाद हमको देखना हीट रेट ऑफ हीट फ्लक्स और हीट फ्लक्स. तो हीट फ्लक्स क्या है? माइनस के इंटू टेम्परेचर ग्रेडियंट. ठीक है, तो एक बार तुमको टेम्परेचर पता चल गया, so you can just take flux is nothing but minus k dt by dr. Okay, and then you just take the derivative of this temperature. ठीक है, so I've done the math. I am not going to explain the math, but finally the flux of heat transfer comes out to be this expression. ठीक है, this expression, it comes out to be this expression. Now what is the now the next step? Now what we have got is, we have got the temperature distribution, we have got the flux. Now what we need to find is, we need to find the rate of heat transfer. तो वो क्या है? That is nothing but minus k into area into dt by dx, or flux multiplied by area. We are just going to multiply by area, but here area is going to be a function of r. It's going to depend कि कौन से r पे हम देख रहे हैं. ठीक है, so here surface area तुम्हारा क्या हो जाएगा? The circumference of that circle or the cross sectional area multiplied by the length of the cylinder, which is nothing but this 2 pi r, 2 pi rl. Okay, so you just multiply by area, and what you end up is, you end up with, yeah, you end up with this expression for heat transfer rate. Okay, q is equals to, you just multiply this thing and you end up with this rate of heat transfer. Okay, I hope there are no questions. Okay, now what are we interested to calculate? We are always interested to calculate first temperature distribution, second heat transfer rate, heat transfer flux, and the third is heat transfer area. So we found this also, we found flux also, we found rate of heat transfer also. Now resistance is क्या होगा? Resistance is going to be total driving force divided by the current is going to, or the rate is going to be equal to total driving force divided by the resistance. तो इसका मतलब resistance is going to be total driving force divided by rate. तो total driving force क्या है? T2 minus T1 और T1 minus T2, whatever. ठीक है, T2 minus T1 divided by the flux rate है ये तुम्हारा, तो यहाँ से आ जाएगा तुम्हारा resistance. ये इसको तुम सिंप्लीफाई करोगे तो ये end up with R is equal to this thing, right? R is equal to ln of R1 by R2 divided by 2 pi kl. T2 T1 कट जाएगा, ये ऊपर चला जाएगा, तो ln R1 by R2 और माइनस साइन यहाँ पे अकोमोडेट हो जाएगा, डिवाइडेड बाय 2 pi k. ठीक है, तो टेम्परेचर डिस्ट्रीब्यूशन एक्सप्रेशन तो पता चल गया, बट हाउ डज इट लुक? इट लुक्स लाइक दिस. इट्स अ पैराबोला, सिंस इट इज अ लॉगरिथमिक, रेजिस्टेंस इज टेम्परेचर, सॉरी टेम्परेचर जो है, देयर इज सम ln हियर, सो इट्स गोइंग टू बी लॉगरिथमिक थिंग. और ऐसा टेम्परेचर डिस्ट्रीब्यूशन होगा तुम्हारा कि R इज इक्वल टू R1 पे टेम्परेचर इज T1, R इज इक्वल R2 पे टेम्परेचर इज T2. ओके, now ये how many resistance, let's say for example you have a 3 cylinders, concentric cylinder. This is one cylinder. इस सिलेंडर के अंदर हॉट फ्लूइड फ्लो हो रहा है, and then we have surrounding this inside cylinder we have a bigger cylinder which is this green cylinder, and then even outside that we have this black cylinder. ठीक है, this hot fluid का bulk temperature is T∞1 and heat transfer coefficient is H1, whereas this इसका जो वो होगा, जो green cylinder का thermal conductivity is K1 and black cylinder का thermal conductivity is K2. So now my question is, how many resistances we have and can we draw resistance resistance network? तो पहला रेजिस्टेंस क्या होगा? पहला रेजिस्टेंस होगा ये जो बल्क फ्लूइड है, इसकी वजह से जो रेजिस्टेंस आएगा, तो दैट इज दिस इज अ फ्लूइड, हम उसको करेंगे निकालेंगे यूजिंग न्यूटन्स लॉ ऑफ कूलिंग. सो दैट इज गोइंग टू बी द फर्स्ट रेजिस्टेंस ड्यू टू दिस फ्लोइंग फ्लूइड. ठीक है, second resistance would be because of this green cylinder, right? So this is the solid, so we'll categorize this using conduction. The third resistance is going to be this black one, ठीक है, and उसको कैसे quantify करेंगे, ये resistance है. And then the fourth one is this cold fluid. So the total there are 4 resistances here. ठीक है, 4 resistances है. How many resistances we have? We have 4 resistances. And can we draw the resistance network? Yes, we can draw the resistance network. कैसे कि यहाँ पे आएगा, सबसे पहले टेम्परेचर T1 है, T infinity 1, उसका रेजिस्टेंस होगा 1/H1A, ठीक है, बिकॉज एरिया इज गोइंग टू चेंज. ये मैंने बोला था स्टार्टिंग में कि अगर तुम्हारा वन डायमेंशनल प्लेन स्लैब है तो उसमें एरिया इज गोइंग टू रिमेन सेम, बट इन circular or spherical system we are going to have different areas, so that is why we can describe different sort of heat transfer, overall heat transfer coefficient. So हम, or that is what we are going to do, we are going to define different heat transfer coefficient, ठीक है. तो 1/H1A, this is nothing but L2 by ln of R2 by R1 divided by 2 pi Q1L, ठीक है. ये बिकॉज ऑफ ये इसकी वजह से जो रेजिस्टेंस आएगा, ये तो पहला रेजिस्टेंस बिकॉज ऑफ दिस हॉट फ्लूइड which we can say 1/H1A, where A1 is going to be this one, which is 2 pi R1, let's say ये R है तो R into L. दूसरा आएगा बिकॉज ऑफ दिस ग्रीन पार्ट, उसको कैसे कैटेगराइज करेंगे, उसको हम क्वांटिफाई करेंगे यूजिंग दिस एक्सप्रेशन R1/2. सो यहाँ पे R1 हो जाएगा तुम्हारा, राइट. सो यहाँ पे R1/R2 हो जाएगा, ठीक. R2/R1, ठीक. थर्ड इज ड्यू टू दिस ब्लैक सिलेंडर, ठीक. ये ब्लैक सिलेंडर की वजह से होगा, दैट वी कैन कैटेगराइज यूजिंग दिस एक्सप्रेशन. एंड द फाइनल वुड बी बिकॉज ऑफ दिस कोल्ड फ्लूइड, इसको हम बोलेंगे 1/H2A2, ठीक है. सो इन टोटल फॉर दिस सिस्टम व्हाट वी हैव इज वी हैव 4 रेजिस्टेंसेस, and then these resistances we can categorize, resistance network is we can say that resistance network is using this. तो आर टोटल क्या हो जाएगा, आर टोटल इज दिस, ये पहला रेजिस्टेंस प्लस दूसरा रेजिस्टेंस प्लस तीसरा रेजिस्टेंस प्लस चौथा रेजिस्टेंस, ठीक है. आर टोटल इज नथिंग बट ये वेयर एच A1 इज 2 pi R1L, A2 इज 2 pi R2L. तो ये तुम्हारा ओवरऑल हीट ट्रांसफर रेजिस्टेंस हो जाएगा. एंड व्हाट वी हैव टू डू इज वी हैव टू फाइंड व्हाट इज द ओवरऑल हीट ट्रांसफर कोएफिशिएंट, बिकॉज कंसेप्ट सेम रहेगा कि हमको, दो वी हैव दिस बट वी कैन ओनली मेजर द टेम्परेचर, दिस मेजरेबल टेम्परेचर्स आर ओनली द टेम्परेचर्स ऑफ द hot and cold fluid. So in this case T1 and T infinity 1 और T infinity 2 ही measurable है, and we want to, what we want to do is we want to completely describe the system using these two temperature. So that is why what we need is we need something called as an overall heat transfer coefficient, ठीक है. तो overall heat transfer coefficient, ठीक है. So now because there are two area, यहाँ पे area 1 है, area 2 है, तो इसलिए मल्टीपल हीट ट्रांसफर कोफिशिएंट्स कैन एग्जिस्ट, ठीक है. यहाँ पे हम 1 सब्सक्रिप्ट यूज कर रहे हैं फॉर इनसाइड एरिया एंड 2 सब्सक्रिप्ट वी आर यूजिंग फॉर आउटसाइड एरिया, ठीक है. सो 1/U1A1 इज इक्वल टू 1 by this is the overall heat transfer coefficient based on inside surface area. We can write this as 1/U1 A1. A1 is equal to 2 pi R1L using this expression. और अगर हम divide everything by 2 pi R1L, so this is what we end up with heat transfer. This is overall heat transfer coefficient based on inside area, ठीक है. सिमिलरली अगर एरिया A1 की जगह हम A2 यूज करेंगे, सो वी एंड अप विथ ओवरऑल हीट ट्रांसफर कोएफिशिएंट फॉर based on outside area, based on outside area, ठीक है. So what we have covered till now is this one. We have seen general energy balance to quantify conduction mode of heat transfer. We have studied one dimensional 1D conduction with q dot equal to 0 in Cartesian coordinate system and radial coordinate system, ठीक है. अभी हमने radial coordinate system पे पढ़ा. Spherical coordinate system, I'll leave it as a homework because whatever we have taught till now, the fundamental way of calculating remains the same. Only the इंस्टेड ऑफ दैट del to t you will use Laplacian का जो expansion होगा, you'll use this spherical one that also I have provided. ठीक है. Now in the next class what we are going to see is we are going to include heat generation. अभी तक हमने हीट जनरेशन नहीं समझा. हम सबसे पहले हमने समझा सिर्फ प्लेन वॉल पे कैसे होगा. उसके बाद हमने कॉम्प्लेक्सिटी बढ़ाई कि एरिया चेंज हो रहा है तो वो कैसे होगा. उसके बाद हमने देखा कि सिलेंड्रिकल कोऑर्डिनेट सिस्टम में कैसे होगा. नेक्स्ट क्लास में हम प्लेन वॉल लेंगे और उसके अंदर हीट हीट जनरेशन टर्म डालेंगे एंड देन वी विल सी हाउ इट इज गोइंग टू अफेक्ट. ठीक है. So with this, I will end today's class. Thank you.